So I did want to also make sure that we hit some examples of the other indeterminate form that the AP exam covers, which is the idea of infinity over infinity. And again, we don't want to actually write it as infinity over infinity. It just is a convenient way for us to speak about the indeterminate form. So if we look at the limit as x approaches pi over 2 of secant of x over 1 plus tangent of x, secant of x, what we have if I try substitution is secant of x is 1 over cosine. So if I plug in pi over 2, that's 1 over 0. That's approaching one of the infinities. And it quite honestly doesn't really matter which infinity it's approaching. It's the fact it's approaching an infinity. If I go down to the bottom here, tangent of pi over 2 is, well, tangent sine over cosine, so I run the same issue. I get 1 plus either positive or negative infinity. So the bottom is also infinite. So again, the way I'm acknowledging that is I'm just showing the top is approaching infinity, the bottom is approaching infinity. This is one of our two indeterminate forms that we can use L'Hopital's rule on. So I'm going to indicate I'm using L'Hopital's rule with a limit as x approaches pi over 2. Still haven't evaluated that yet. And then I work on my derivative. So that's going to be the secant x tangent x. On the bottom, derivative of 1 is 0. Derivative of tangent is secant squared. I'm going to simplify that a little bit just to clean it up some. So that's the limit as x approaches pi over 2. One of the secants cancel, leaving me with tangent over secant. But if I think of those as sines over cosines, that's the limit as x approaches pi over 2 of sine of x over cosine of x, all divided by 1 over cosine of x. That does simplify as well to the limit as x approaches pi over 2 of sine of x, which gives me 1. And there is our limit. Aren't you glad we didn't have to try to do this with more algebraic simplification and the properties of trigonometry? If I look at my next example here, the limit as x approaches infinity of the natural log of x over 2 times square root of x. We can't actually plug in infinity, so when I talk about doing substitution here, it's the idea of plugging in ever larger numbers. And as x gets larger and larger and larger, the natural log of x will also continually get larger. So although this is going to be very slow, the natural log of x does also approach infinity as x approaches infinity. And same thing happens with the square root of x. As x gets bigger, square root of x is going off to an infinite value as well. So this is one of our indeterminate forms where the numerator is approaching infinity and the denominator is approaching infinity. So I can apply L'Hopital's rule. So I indicate I'm using L'Hopital's rule. I still have not found the limit yet, so I have to rewrite the limit notation. Derivative of the top would be 1 over x. Derivative of the bottom, remember this is 2 times x to the 1/2. So I can use power rule, bring the 1/2 down, 2 times a half cancels and leaves just 1. Base stays the same, raised to the negative 1/2 power. I'm going to do a little simplification again, just to make this a little bit easier to work with. Remember, the AP exam does not require you to simplify, but a little simplifying when you want to work with what you've done is not a bad idea. So the limit as x approaches infinity of 1 over x all over 1 over square root of x, which when I do that division gives me the limit as x approaches infinity, the square root of x over x, which is the same as the limit as x approaches infinity of 1 over the square root of x. Again, I'm going to try substitution. Obviously, infinity is not a real number, so the idea behind this is I'm plugging in ever larger values. So I have 1 over something that's getting larger and larger and larger. So because what I'm approaching is what's getting larger is always positive, I have 1 over a positive number that's always getting bigger. So like 1 over a million, 1 over a billion, 1 over a trillion. And this approaches 0. And there is our evaluated limit.